Okay, so this is section 15.8, video number 2. So I think we got 5 more examples here, so I think we're going to probably work through the first 3 completely, and then the last 2, just in order to save a little bit of time, we'll get through the setup of, but after that, the work is pretty easy, so I'll probably just give you what the answers are to those, and then if you want to practice working through the triple integrals to make sure you get it, you can do that. I think we'll do it that way. Depends on the time. We'll see. All right, so let's see. Example number 4 here. We want to evaluate the triple integral of e to the z dv, where e is enclosed by the paraboloid z equals 1 plus x squared plus y squared, the cylinder x squared plus y squared equals 5, and the xy plane. All right, so this one we probably want to give a little sketch to. So let's see, that paraboloid is your standard paraboloid, but because of the 1 plus, it's been shifted up 1 unit. So it's going to look something like your bowl, but it's going to be something up in this range, something like that. So that's your paraboloid. The cylinder, that's just your standard cylinder around the z-axis with a radius. It looks like radius is square root of 5. That's kind of a weird one for us, but okay. And it's got to be above the xy plane. So it's going to start down here, something like this. And then it's going to go up, and it's going to meet that paraboloid someplace up there. So basically, that paraboloid, I guess, is going to kind of sit inside the cylinder. So the cylinder is going to be like this, and then on the other side, it'll still kind of look like this. But we want everything which is underneath of that paraboloid and above the xy plane up to there. So that's what we're looking at. Let's see if we can kind of highlight the area here, so, or the volume. So we are looking for everything in this region right here. And we are taking the integral of e to the z power, so we are finding mass here. All right, well, let's see if we can figure this one out. This one actually doesn't look like it's going to be that difficult to do. So again, it's around the z-axis, so the z part is going to go from 0 up to that function right there, which is kind of hidden now inside of my paraboloid drawing. Should have shifted that down a little bit. But we can rewrite that one in terms of polar. So let's go ahead and do that. Again, the polar part's probably the easiest part here. So again, it's circular, so it's going to go 0 to 2 pi for theta. The r is only going to go from, again, from the center here out to the edge, and it looks like that's going to be a square root of 5 according to that equation right there. So we're going to go 0 to the square root of 5. That's our r part. And then again, z is going to go from, looks like z equals 0, that's the xy plane, up to z equals 1 plus x squared plus y squared. Again, x squared plus y squared is r squared, so that's 1 plus r squared. So now we have to put e to the z dz, that's the inside one, and then r dr d theta for the polar part. All right, no shortcuts, at least not in the beginning here. So we're just going to have to take the antiderivative of e to the z with respect to z. Fortunately, that's e to the z. So we'll rewrite the outside 2 parts. Antiderivative is e to the z evaluated from 0 to 1 plus r squared. R dr d theta, and yes, I could have brought the r into the other part. At this point, it doesn't matter. We'll get to that. You do have to be careful here because, yes, I do have a 0 as a bound, but remember, this is going to be e to the 0, so it's not going to make it 0. So let's see, we get integral 0 to 2 pi, integral 0 to square root of 5, and then I'm going to plug in 1 plus r squared, so we get e to the 1 plus r squared minus e to the 0, but that's 1, r dr d theta. Okay. In order to do this next part, you could do this in multiple ways. First thing I can see is I've only got r's left, so I can definitely split off the theta. Let's do that. 0 to 2 pi of d theta times integral from 0 to square root of 5. Probably the best thing to do here is to separate these two integrals. I'm going to distribute the r. So you're going to get r e to the 1 plus r squared dr minus the integral from 0 to square root of 5 of r dr. And that's distributing the r and then separating them. And you might ask, well, why am I doing that? Well, it's because the middle part, we're going to have to utilize u substitution. So you kind of do need to split these things up to do this. So let's go ahead and write out what our u substitution is going to be. The composite piece is 1 plus r squared. So du then becomes 2r dr, or dr is du over 2r. Let's go ahead and make our substitutions. We can do a few things at once here. 0 to 2 pi of d theta, we know that's 2 pi. Let's make our substitutions. So that's going to give us r times e to the u times the new dr, which is du over 2r. I'm going to go ahead and change the bounds. This is why the square root of 5 here is not so bad. If I plug 0 in for r, we're going to get 1 for the lower bound. If I plug square root of 5 in for r, we're going to get 1 plus square root of 5 squared, so 1 plus 5 is 6. And then it's minus, should probably put brackets around this because the first integral is being multiplied by this whole thing here. Minus, let's see, that's going to be 1/2 r squared from 0 to square root of 5. All right, let's simplify. The r's are going to cancel out. I can pull a 1/2. Actually, I can pull a 1/2 out of the entire thing because I've got a 1/2 here. Got a 1/2 here. Let's pull the 1/2 out to the very front, multiply it by the 2 pi. So really that just leaves us with a pi on the outside. That's nice. And then I can take the antiderivative of e to the u, which itself is e to the u, evaluated from 1 to 6, minus r squared, r squared, evaluated from 0 to square root of 5. So let's see what we get. This one's not going to end up being very pretty. So we're going to get e to the 6th minus e to the 1st, or e, minus r squared at square root of 5 is going to give us 5, minus 0 is just 5. So it looks like if I did that correctly, we're going to get pi e to the 6th minus pi e minus 5 pi. Not a very pretty answer, but that is the answer. All right, moving on. Let's evaluate the triple integral of x squared dv, where e is the solid that lies within the cylinder x squared plus y squared equals 1, above the plane z equals 0, that's the xy plane, and below the cone z squared equals 4x squared plus 4y squared. All right, well, let's sketch it first, then we'll deal with the conversion stuff. So we are going to find the triple integral. Let's see, it lies within the cylinder x squared plus y squared equals 1, and above the plane z equals 0, and below the cone z squared equals 4x squared plus 4y squared. Let's solve that for z so we get it in the right form. So that's going to be z equals the square root of 4x squared plus 4y squared. I don't need the plus or minus because it does say above the plane z equals 0, so we're only talking about the top half of the cone. All right, so let's see. What is that going to be? I can factor the 4 out, which is going to give me a 2 on the outside. So that's 2 times the square root of x squared plus y squared. In polar, however, x squared plus y squared is r squared. So really that gives me 2r. So we're going to have our cone, which looks something like this. So we want to find this triple integral below that cone, but within the cylinder, x squared plus y squared equals 1. So, maybe that's only out to here. Who knows? Because the cone is going to keep on going, but maybe we're only trying to find the space in that cone. So really what we're looking for is the space from the xy plane up to this cone. So again, I'm going to use a little highlighter here just to highlight the portion that we're looking for. So we are only looking for, I'm not very good at staying within the lines. We're only looking for basically that section right there. All right, well, it really shouldn't be too difficult to set up because we've already done the conversion here to polar. I said I was going to do that later, but it ended up being easier to see it like this. So, triple integral. Again, it's a circle, so 0 to 2 pi. The radius, let's see, the maximum the radius is. Remember, the radius is going to go from the center of the cylinder part, which is in here, out to the edge. Well, the furthest the radius can go is up here, out to that point right there. So it looks like that radius is going to be 1. That's the biggest the radius can be. So we're going to go from 0, oops, try that again. We're going to go from 0 to 1. Could be smaller, which is why it's in between 0 and 1. And then z itself is going to go from 0, which is the xy plane, up to 2r, because that's the bottom of that cone, or that cone. And we are doing x squared. Now, we do have to convert x squared into terms of polar. If that was a z, no problem. We leave it as z because z is z in this case. But since it's x squared, we might need to change it to polar. And don't forget that x is r cosine theta. So if I square that, I'm going to get r squared cosine squared theta dz r dr d theta. All right, let's go ahead and simplify that just a little bit. Let's combine the r's. Whoops. So we're going to have r cubed cosine squared theta dz dr d theta. And if that r in the bounds was not a constant, if it wasn't there, it was just a constant, we could separate all this stuff, but we can't. So let's go ahead and do the z part first. So antiderivative of all this with respect to z is just going to put a z on there. So z r cubed cosine squared theta from 0 to 2r dr d theta. So plugging a 2r in for z, we're now going to get 2r times r cubed, which is 2r to the 4th cosine squared theta. Plugging a 0 in for z wipes that rest of that out. So now we should be good to separate these things. I've got all constant bounds left. The variables are separable, so we're good. We can separate this. So we're going to have our good old friend here, 0 to 2 pi of d theta. And we're going to have, oh, we're not actually going to have d theta. That would have been really nice. We do have something to integrate there. Cosine squared theta, d theta. Still can separate them. And then 0 to 1 of 2r to the 4th dr. All right, the cosine squared. In order to integrate cosine squared, we have to remember the identity which reduces a cosine squared function. And the identity for that one is 1/2 1 plus cosine of 2 theta. That is cosine squared. We need that to reduce it from a squared to a non-squared term. It's easier to take the antiderivative that way. And then the right side here, we can go ahead, or not the right side, but the right integral here, we can go ahead and integrate. That's going to be 2/5 r to the 5th from 0 to 1. All right, let's take the antiderivative of the left integral. So you're going to have a 1/2 times integral of 1 is theta. Antiderivative of cosine of 2 theta is sine of 2 theta times the reciprocal of the 2 theta part, which is going to be the 1/2, this reciprocal of that slope, from 0 to 2 pi. And then plugging a 1 and a 0 in for r is going to give us 2/5 minus 0, or just 2/5. So let's plug in the 2 pi and the 0. This one actually is going to simplify very nicely. So you're going to get 2 pi. Sine of 4 pi is 0. Sine of 0 is 0. And theta evaluated at 0 is 0. So the rest of that stuff just gives you 0. So 2/5 times pi is pi. 2/5. Try it again. 1/2 times 2 pi is pi, times 2/5 just gives you 2 pi fifths. Okay, it kind of started off a little bit more rough with that one, but overall not too bad. All right, one more that we'll actually complete, and then the last two, like I said, I think we'll just set them up, and then I'll let you work them out on your own if you want to, but I'll give you the answers. So, example 6, find the volume of the region E bounded by the paraboloids, which are given as z equals x squared plus y squared, and z equals 36 minus 3x squared minus 3y squared. Wow, okay. Z equals x squared plus y squared. That's a pretty standard paraboloid. That one's going to look something like this. Whoa, I missed completely on that. Let's try that again. It's going to look something like that. And obviously it'll keep on going. And then z equals 36. Boy, did I draw this in a bad place. 36 minus 3x squared minus 3y squared. So if you want to rewrite that one, you can rewrite it as 36 minus 3 times x squared plus y squared. That might help. But ultimately, this one starts at 36. This will not be drawn to scale. This is going to start at 36 and then open down. And that's because the x squared and y squared are both technically negative. So this thing is going to start way up here and open down. And at some point on these things, because it's going to keep on going, at some point, these two paraboloids will intersect. Basically, all along this red line here, these things are going to intersect along that red curve. And that's going to be important because where they intersect, because what we're looking for is the region bounded by these two. So if I sketch, let's go ahead and highlight this again. If I put this into the highlighting part, this part is bounded by it. And this part down here is bounded by it. So all of this kind of egg-looking shape thing right here is bounded by those two paraboloids. Now the green one, the paraboloid that opens up, technically keeps on, oops, it's supposed to be in green, technically keeps on going in that direction, and obviously rounds itself off at the top as well. So we're only looking by the inside parts there. The reason that intersection is important is because that's going to, for one, it's going to determine our R value. That's probably the most important part about this whole thing, actually. The radius, the maximum radius is going to go from here out to where these two things intersect. That's going to be the maximum radius you can have. Obviously, the radius could be smaller. It could be this radius. It could be smaller up here. It could be that radius. But the radius, the maximum radius, because it's going to go from 0 to something, is where those two things intersect. So we do need to figure that out. And in order to figure that out, we're going to have to set the two equations equal to each other. So I know that x squared plus y squared is going to have to equal 36 minus 3 quantity x squared plus y squared. Okay, and actually factoring that out helped me quite a bit, because now I'm going to add 3 of the x squared plus y squareds to the left. So now I get 4 x squared plus y squared equals 36, or dividing by 4, we get that x squared plus y squared equals 9, which tells me that the maximum radius of that intersection is going to be the circle with a radius of 3. So the radius there of that specific circle is going to be 3, and that's pretty important. And z itself is going to go from, it's maybe an orange, is going to go from this bottom paraboloid up to the top paraboloid. So we just need to make sure that they're both in terms of polar. All right, so let's set this up. Our triple integral. Again, we know theta will go from 0 to 2 pi. We just figured out the radius is going to go from 0 to 3. And the bottom paraboloid is z equals x squared plus y squared, which is the same as z equals r squared. So that's r squared. And the top paraboloid is this one, which is, again, just replacing the x squared plus y squared with r squared. So it's 36 minus 3r squared. 36 minus 3r squared. And it says find the volume. So we are integrating with a rho value of 1. So we don't have to put anything there. So it's just going to be dz r dr d theta. All right, so let's go ahead and work this one out. I'm not sure how nice this one will be at the end. We'll find out. So the antiderivative, start off with the z part, is going to be z from r squared to 36 minus 3r squared, r dr d theta. So plugging this stuff in, we're going to get 36 minus 3r squared minus r squared, r dr d theta, integral 0 to 3, integral 0 to 2 pi. Okay, I definitely only have r's and thetas left, so now we can do our standard integral 0 to 2 pi of d theta part. And then we're going to have the integral from 0 to 3 of 36 minus 4r squareds. Whoops, let's actually go ahead and distribute the r through there. So that'll be an r there and then an r cubed there, dr. So we know we'll get 2 pi from the first integral. Now we have to actually go ahead and do the antiderivative. So the antiderivative of 36r will be 18r squared. Antiderivative of 4r cubed is just r to the 4th. Okay, that's actually not so bad, from 0 to 3. This will work out to be relatively nice. Okay, so we get, whoops, I hate when that happens. So we get 2 pi times, let's see, it's going to be 18 times 3 squared, 18 times 9, 72, 162, I believe, 162, minus r to the 4th, which is 81, because that's 3 to the 4th, and then 0 gives us nothing. So 162 minus 81 is 81, times 2 pi is 162 pi. So that's the volume that's caught in between those two paraboloids, kind of that egg-looking shape that was up there. Okay, video is definitely running longer, but I do want to just set these last two up. Doesn't make sense to do a video for the setup of these last two. All right, evaluate the integral by changing to cylindrical coordinates. So really all it's asking us to do is recognize what these coordinates are and change it. Well, let's see. Z is the inside piece. So we know Z is going to go from x squared plus y squared to 2 minus x squared minus, that should be a y squared. I think it says y to the x, but that should be a squared there. So change that. That should be a squared. So changing the z part really should not be difficult, because that's just going to be r squared in the bottom and 2 minus r squared in the top part of the integral. So r squared to 2 minus r squared. That's the z part. That right there, if you were to sketch that, it's saying x goes from -1 to 1, and y, which is the middle part, is going to go from this thing right here to that one right there. Well, the upper one is the top half of a circle with a radius of 1. The bottom one is the bottom half of a circle with radius of 1. So this is just a circular domain in the xy plane with a maximum radius of 1. So the radius will go 0 to 1. Theta will go 0 to 2 pi. Okay, I do have to replace x squared plus y squared in terms of polar, but that's r squared. So you get r squared to the 3/2 power, multiplying the exponents, you really just get r cubed. R cubed. And then don't forget it's dz, replace the dy dx with polar, which is r dr d theta. And then obviously you can multiply the two r's together and get r to the 4th. Evaluating this one, again, is not horrible. I will tell you that the answer of this should be 8 pi over 35 if you want to go ahead and work it out and check it. All right, and then the last one. This one actually says evaluate, but once again, you kind of have to recognize what's going on. It's the same general idea as what we just looked at. This last piece, the yz part, sorry, the yx part, is telling us that, let's see, this represents the top half of a circle, that represents the bottom half of a circle with a radius of 2. And the x is going from -2 to 2. So once again, your domain in the xy plane is a circle with a radius of 2. And then the z part, well, x squared plus y squared is r squared, so that's going to be the square root of r squared, so that's going to go from r up to 2. The constant doesn't change, that's just a flat plane. So it really shouldn't be that difficult. Let's see, we're going to have 0 to 2 pi for theta, 0 to 2 for r, and then z is going to go from, again, square root of r squared is r up to 2. X squared plus y squared here for our density function is r squared, so it'll be r squared dz r dr d theta. So it is important to be able to change these things if necessary, because as it stands right now, that triple integral dz dy dx, it can be done, it's just messy. And I will tell you that the answer to this one, once again, is 16 pi over 5. Not terribly difficult to do once it's set up. All right, plenty enough for these two videos, and that should get you through 16.8. 15.8, correction.